subject is GCSE physics. This is atomic structure lesson 11, and this one's gamma radiation and electric and magnetic fields. Objectives are to recap ionisation, but you probably already know what that is, and methods of radioactive decay, an explanation of what gamma decay is, and how do alpha, beta and gamma behave in electric and magnetic fields. So ionisation. Ionisation occurs when an atom loses one or more of its electrons. And when you lose an electron, obviously you would then have an excess of protons in the nucleus, so the atom would then become a positive ion. So there's an uncharged lithium atom. And an atom has, by definition, or part of its definition, has the same amount of electrons as protons, and that's because they're electrically neutral. So if you've got 3 protons, that's a charge of +3, and if you've got 3 electrons, that's a charge of -3. +3 minus 3 gives you a charge of 0. So there's a positive ion for lithium. As you can see, one of the electrons has been removed, and now there's an excess of protons. So you've got 3 protons and 2 electrons, which gives a relative charge of +1. Alpha particles, they cause intense ionisation due to their large mass and their double positive charge. Remember, an alpha particle is 2 protons and 2 neutrons, a helium nucleus. Beta particles cause moderate ionisation, and gamma rays only cause weak ionisation, and one of the reasons is that they are uncharged. Remember to pause and take any notes if you need to. Let's move on. So what is gamma decay? So gamma decay is the emission of electromagnetic radiation from an unstable nucleus. And gamma radiation often occurs after a nucleus has already emitted an alpha or beta particle. So basically the atom that's remaining after the emission of alpha or beta would have excess energy, and it gives off that excess energy as an electromagnetic wave. So an example, cobalt-90. So cobalt-90, 27 protons, mass number of 90, would still be cobalt plus gamma. So cobalt-90 with excess energy decays to cobalt-90 with less energy plus gamma radiation. And instead of this symbol, for gamma, you could use this one. It's exactly the same. Well, not the same symbol, but means the same thing. All right, let's do a little exercise. So let's pause this, have a go, write down what happens, and then I'll take you through the answers. So changing elements, both alpha and beta decay, cause the anisotope. Yeah, that's definitely shouldn't be there. Cause an isotope to change atomic number and therefore elements. Remember, we talked about this in previous lessons, that if you change the proton number of an element, then that's what gives you a different element. And the periodic table, literally goes hydrogen, helium, lithium, beryllium, boron, carbon, and all that happens is that the proton number increases by 1 each time. And therefore element. So alpha decay also causes a change in mass number. So what about alpha? What happens to atomic number or the proton number? So it goes down by 2. What about the mass number? Well, an alpha particle is 2 protons and 2 neutrons, so the mass would go down by 4. Beta particle. Now you've got to remember, beta radiation is where a neutron will convert into a proton and eject an electron from the nucleus. So that means the atomic number or the proton number will go up by 1. The mass number will stay the same because we've just had a neutron turn into a proton. What about gamma? No change in atomic number and no change in mass number. Hopefully that went okay. If you're struggling with the properties of alpha or beta, there's a previous lesson in the atomic structure playlist where it's explained, or where they're both explained. Let's have a go at this one then. Right, we've done some of these before. Or you should have if you've done them at school or done a previous video lesson. Decay equations, so I need to pause and have a go at this one. So complete the decay equations below. So the first one, Fe, that's iron, into cobalt plus a beta particle. So the numbers, so we've got the mass number for beta decay doesn't change. We end up with an extra proton because a neutron turns into a proton. And then obviously we've got to make this balance, so we need a -1. 27 minus 1 on the right hand side gives us 26 on the left hand side. So the next one is alpha decay. So the top one is obviously 220 because 220 plus 4 is 224 on the left-hand side. And the alpha particle has obviously got a mass of 4 and a proton number of 2. And then you can work backwards and calculate the 88. So we've got 88, 220, and 2. Hopefully that's okay. You don't need to know the symbols, what they are. And in an examination, you wouldn't be expected either. It'll probably just give you, it'll either give you the RN or the RA, or the CO or the FE, or it will just put the letter X. So next one, should have got 16 on the top, and the particle that's missing, 0 minus 1, is obviously the same as the beta particle at the top, is there. And that O was missing. You don't need to know what, the oxygen has 8 protons and 8 neutrons. Right, let's look at deflection by magnetic fields. So a magnetic field you can really just think about as a literal magnet. All right, so we've got alpha, beta, and gamma. And when you put them near a magnet, the alpha particles will deflect slightly. And you don't need to know which direction at GCSE at all. You just need to know that alpha will go one way and beta will go the other way. And if you want to think about why that might happen, it's pretty obvious. It's the fact that alpha particles have positive charge and beta particles is just an electron has negative charge. So due to the charges, they will move in opposite directions. So alpha and beta particles are deflected in opposite directions due to their opposite charges. But why does beta move, why is it deflected more severely than the alpha radiation? And it's quite straightforward. Due to their much larger masses, or much larger mass, alpha particles are deflected far less than beta. An alpha particle is just under 8,000 times more massive than a beta particle, which is an outrageous amount. So, I don't know, for example, just to give that some figures, if you had a mass of a kilogram, say that your body mass was 1 kilo, the equivalent human that's 8,000 would have a mass of 8,000 kilograms or 8 tons. So it's a big difference. Hence the more severe deflection for the beta particle. And gamma rays, because they're uncharged, because they've got no charge, they are not deflected. They just pass straight through a magnetic field. All right. So if you want to make notes, remember to pause. Let's move on. Let's look at electric fields. So deflection by electric fields. So we've got alpha, beta, and gamma again. And this happens. Now, for electric fields, the alpha and the beta go in opposite directions, but this time you need to actually know which direction, and it's pretty straightforward. An alpha particle obviously has +2 positive charge, so it would naturally be attracted towards the negative side of the electric field. And the beta particle is a fast-moving electron which carries negative charge, so obviously that would move towards the positive side of the electric field. So alpha and beta particles are deflected in opposite directions due to their opposite charges. And due to their much larger mass, alpha particles are deflected far less than beta. That's the same reasoning for the magnetic fields. And lastly, the gamma rays, once again, are not deflected because they are not charged. All right, let's finish with a closed exercise. So you can either write this out in full with the keywords, or you can just write 3, 4, 5, 6, 7, 1 to 9 and put the keywords in the right place. It's completely up to you. So there's the keywords. If you want to pause and finish this one off. And then I'll take you through the answers. So magnetic and electric fields deflect alpha and beta particles in opposite directions due to their opposite charges. Beta particles deflect more because their mass is about 8,000 times less than alpha particles. Gamma rays, being uncharged, are not deflected by either type of field. Then back to a previous lesson. Radioactivity causes ionisation, which we touched on earlier, which can cause living cells to undergo genetic mutation, leading on to possibly cancerous growth. It is therefore important to minimise exposure, especially to alpha particles, which cause the most intense ionisation. Now, you might be thinking there, and rightly so, that alpha particles obviously cause the most ionisation, but it's also the easiest to keep away from the human body. If you just wear some gloves, the alpha can't get through the glove material, can't even pass through paper, and can only pass through a couple of centimetres of air. So directly outside the body, the most dangerous one would be the beta radiation, as beta radiation is quite a much larger range in air, approximately 1 meter, and it can get into pass into the human body because you need stuff like aluminium to stop it, and it's still got quite intense ionization properties. And gamma radiation, we just pass straight through. But fortunately, the ionization power of gamma radiation is significantly less than alpha or beta. Anyway, I hope that helps. Thanks for watching, and I'll speak to you soon.